Hi everyone, it's me, Carolyn, and in this video we are going to start talking about hypotheses testing. Now, this is something that happens a lot of the time in research. Now, I'm not sure exactly how technical they do if they write out all the steps, but these are the steps that they go through. Whether or not they actually physically write them down is something that I am not familiar with because I haven't really talked to someone in that field. But this is what happens when they are trying to determine if a new product is going to be better than the old, some of the testing that goes through. So we're going to just get a brief introduction to some of this. We'll see a few examples. Now, again, these examples are completely made up. They are not real world examples. Some of them may be historically real world examples. So I've pulled them from textbooks, just so that you know that sometimes they are somewhat real. Okay, so first of all, when we do hypotheses testing, what they're going to be looking at is whether or not a parameter has increased or decreased or changed. So some of the parameters that we have seen so far, we've talked about the population mean. So we've looked at calculating probabilities based on it, looking at the sample means. We've looked at finding confidence intervals for this mean. We've talked about the standard deviation, and we've talked about the population proportion. There are lots more measurements that are out there. We are just touching on a few. But a statistical hypothesis is basically a statement or a guess or a conjecture about this population proportion. And the statement can be either true or not true, and that's what they're going to be testing. So all hypotheses tests are going to be the same. We're going to be trying to find out if there is significant or enough evidence given by our sample. So what they'll do is they'll make a guess as to thinking, okay, this drug is going to be better than the old drug because headaches will be cured faster. So they're going to think that time that a person has a headache will decrease once they've taken this drug. So it'll be gone faster. So they would take a sample, do their testing. They'd have some control groups and all these sorts of things, and they'll be testing one group maybe versus another and things of that nature. So all that stuff goes into these hypotheses tests. We're not going to be doing the actual experiment part to get the data. We'll just have the results of the data to help us walk through the process. So the first thing they do is they are going to have two statements. They're going to have a null hypothesis and an alternative hypothesis. We use H with a little zero down here for the null being the zero. That's going to be our status quo, kind of what we believe is the truth as we see it right now. And then we're going to be having this alternative. In our textbook, we use an HA. I have seen some use a capital A, and I've seen some textbooks use a 1, versus the 0. And I'm going to jump right into writing these hypotheses so we can kind of get a feel for what we're going to be doing. And then we'll actually go through the whole process. So the first one that I have is we have a researcher thinks that expectant mothers will use vitamin pills to, they do that the birth weight of their babies will increase. So the current birth weight of babies is 8.6 pounds. So the null hypothesis is something, first of all, we have to identify the parameter that we're talking about. And we are talking about average birth weight. So that means we are talking about the mu, the mean, the average. And since we're thinking that average birth weight, the belief is right now that it is 8.6 pounds. So right now, that's the status quo. That's what we're trying to disprove, so to speak. Because we feel, or this researcher feels, that if they take these vitamin pills, that this birth weight will increase. So increase means it's going to get bigger than that 8.6. Some things to kind of notice when we're writing our hypotheses, this first one will always be an equal to symbol. Whether it's equal to a number, or if we're comparing two sets, one set would be equal to the other set. The second one is going to be either a greater than symbol, a less than symbol, or a not equal to symbol, depending on the words we see in the process. The other thing is this number, if it is compared to a number, will always remain the same from one to the next. All right, let's do another one. So the lifetime of a light bulb is said to last on average, so there we're talking about an average of 1,000 hours. A consumer research firm believes that light bulbs do not last that long. So again, our hypotheses. Again, we're talking about the average, so we do have that mu in there, and it's going to be equal to, and the number that they think that it currently is 1,000. However, our research firm believes it is not that long, so smaller than that 1,000. Okay. If we had said something like that they just believe that it is not 1,000 hours, the H alternative would have just been that not equal to 1,000 hours. So that's kind of the first step for these hypotheses. First of all, trying to find out what is the status quo, what we believe things are right now, and then what do we believe we're trying to prove? Are we proving it is greater than, it is equal to, not equal to, less than, or greater than? So the symbols. So sometimes we have to be very careful when we're reading these problems. And so what I've done is I've created a list of some of the common words. This is not a complete list by any means, that could stand for this greater than. So we could hear the words greater than. We could hear more than, at least, increased, like we did in our one example. Heavier, something got heavier. It's larger, it's longer, it's bigger. It's higher, it's faster, it's above, it's taller. Less than would be the less than, decreased, at most, smaller, lighter, shorter, smaller, lower, slower, below. And then our not equal would be, of course, the not equal, does not equal, is not the same as different or will change. When we have these, we will have some what we consider tails, because we will be looking at our two common curves that we've seen so far. We will be looking at our normal curve, our T, are the two that we'll be looking at. And all of those, they kind of look the same. They are symmetric and a single hump in the middle. And if we have a greater than symbol, we're going to be looking in that upper tail. If we have a less than symbol, we'll be looking down in a lower tail. And of course, the not equal to will look both directions. Okay, there are 5 steps that we go through in a hypothesis test. Okay, and a lot of the times when we do this, when we get to the end, we have to make a conclusion. Was there enough evidence to support that alternative? When we do that, we basically are deciding to reject the null being our H naught. So are we going to reject that null? Which means I kind of like to relate this to our court system, because if we reject the null, we have do not reject the null, we find them not guilty. If we reject the null, we find them guilty. So we never accept the null. We never say that that is true. We will say it is not true. So that means found guilty. Or we will say that it is not found, not rejected. So that means we are not guilty. We never say innocent in the court system. Similar idea here, because we haven't proven that the null is true. We just haven't been able to prove that it is not true. There's not enough evidence beyond a reasonable doubt to reject that null hypothesis. And we'll see some of the conclusions that we write up when we do this. So a lot of times we're trying to prove that alternative. So the first steps that we do is we will state that null or alternative hypothesis. The second step, which does take a lot of time, is to choose the appropriate test and to verify our conditions for that test. Right now, we only have discussed two possible tests. We've talked about a z, the normal, and we've talked about the t. And we've talked about the conditions that are needed for those, and those will be the same in this situation as well. So when we're talking about the mean, if we know the population standard deviation, we will be using our z, provided that it is also a large enough sample. If we don't know our population standard deviation, we use our t distribution. So step 3, when we're talking about the mean, this is what we're going to be looking at here, is we will look at either the z, and when we do that, we would kind of find this test statistic, kind of like a standardized value and taking our sample mean minus this mu0, and I'll talk about that in the example we go through, divided by this population standard deviation divided by the square root of n. Or we would take the x bar minus our mu0, s over the square root of n. And if we've taken a sample, we would have both x bar and s from that sample. This piece here, a lot of times is not known because we don't usually have the population standard deviation. So most of the time in the real world, the t is used over that z. Now, I also want to remind you that when we are talking about a t, we could have some degrees of freedom using n minus 1. However, we will be using SALT for a lot of this, so we won't have to do a lot of the calculations. We will have to do it if we are talking about a normal curve. So our standard normal curve, we will have to do some calculations here. Otherwise, the calculations are built into our system. And we don't have to do all of this calculation. We just have to remember that sigma divided by the square root of n piece. The fourth step, which is usually pretty easy, is to identify our significance level. This is going to be stated in our problem. It is going to be our alpha value. And that is pretty easy. And we're also going to find that critical value. Now, whether you put this in step 4 or step 5, really doesn't matter. The critical value or the p-value, which is the method we'll use, is finding that boundary value that if our sample is in that tail far enough, then we're going to reject. So it's kind of setting up the boundaries. Most software nowadays does find our p-value. The p-value is going to be associated with that test statistic, hence why they usually calculate it. The critical values is more of a historical method, and that is associated with the alpha level, which is stated in our problems. But again, we will go through examples and kind of walk through all of the steps to decide what we're going to do. Step 5 is to make our decision to reject the null or to not reject the null. And I will set up the guidelines to how to determine that. And then once you've made that decision, you're going to write a conclusion that makes sense for the problem, because this would be something that you might publish to the general public. So let's do an example. So let's look at that light bulb problem that we had. So we have these large shipments of newly designed light bulbs are being tested before they're shipped out. Light bulbs are said to last 1,000 hours with a population standard deviation of 20 hours. A quality control manager suspects that changes in this design may have reduced the duration that they last. So they take a sample of 32 light bulbs and they've lasted 900 hours. So that is some of our pieces. That's from our sample. Assuming that the standard deviation has not changed, do we have significant evidence at alpha equal to 0.05 to conclude that the light bulbs last longer than stated? Okay, so we're going to go through our 5 steps. So step 1 is to write our hypotheses. So we have our null and our alternative. So again, we are talking about the average length of time that our light bulbs last. So we're talking about mu. That's our average. And we always start with an equal to, and in this case, light bulbs were said to last 1,000 hours. So we're going to have 1,000. However, this quality control manager thinks that time has been reduced. So less than 1,000 hours. So that's step 1. Step 2 is to determine what test we're going to run. Since we're talking about the mean, we will either use a normal or a t, and a lot of that is determined by what we know or don't know. We know the population standard deviation because it's right here in our problem. And we are supposed to also assume that it didn't change. So we know this. Also, our n was 32, which is bigger than that magic cutoff of 30 that we talked about in earlier chapters. So that means we will be able to use our normal curve. If this had not been 30, we would not have been able to use the normal. We talked a little bit about what we would do. There are other tests that you can do in the cases where there is not a large enough n. If it were me in this situation, I would have just made sure to make, when doing this, and a statistician would know this, to make sure that our sample size is big enough. So making sure to test at least 30 light bulbs, and that so that they could use the normal curve. Okay, step 3 is to calculate that test statistic. And we will be looking at a z. So going back up to my formula, I'm going to kind of put this in here, x bar minus mu 0 all over sigma square root of n. My x bar, that is the sample average. That is the 900 that we had. The mu 0 is the number that's in that hypothesis, that null hypothesis, hence the 0. They kind of match those up. So we're going to be subtracting that by 1,000 because that's what we assume mu to be. And then our sigma was 20 and our n was 32. So I'm going to calculate this number. So making sure to take my 900 minus the 1,000, getting that value first before I do my dividing. And when I divide, I want to make sure to put extra parentheses around this to make sure I'm taking that value divided by that whole part. So I'm going to take divided by. So what I usually do is I'll take my 900 minus my 1,000, get that value, and right now I'm looking at a negative 100. And then I'll hit my divided by key, and in parentheses, 20 divided by, clear. Sorry, my fingers are not working today. Divided by 20, divided by the square root of 32. 32. Okay, so I'm going to show you kind of what I've got typed in there. There's that negative 100 that I had before, and divided by parentheses 20 divided by the square root of 32. This extra set of parentheses is needed, so make sure to put them in there. Then I'm going to hit the equal button. And I get this negative 28.28, and I'm just going to leave it right there because that'll be far enough. I want to remind you that this is a standardized value. So this tells me that this value is 28 standard deviations below our assumed mean. Okay, we're assuming that the mean is 1,000. This 900 is 28 standard deviations below this. So under this assumption, this value has a very small chance of happening. Thinking of our normal curve, and we're in that one little tail. And that's what we find in step 4, is that p-value that we talk about. So first thing we're going to do is identify the alpha. That's this 0.05. And this is something that statisticians and whoever's doing the testing will decide on. The smaller the alpha level, the stronger your test is, because you're making sure that you're really going to be confident. You're like 90, this was like a 95% confident that I'm giving you the right answer. Okay, because you can always be wrong, because we can always get a bad sample. Maybe we got the wrong 32 light bulbs. The other thing we calculate is this p-value that they talk about, okay? And so if you're ever doing reading, like statistical reading or research reading, they talk about p-values. P-value is, so under our assumption, okay, and I'm going to draw a picture, my pen just ran out. So let's grab another one. See that it didn't want to show up very well here. There's a better button. Okay. So under our assumption of this being centered at 1,000, and we had a sample of 900, the p-value is going to be the area associated with this value, that 900, and the direction that we're testing. So the p-value is going to be the probability of getting that number or smaller. So our p-value is the probability that x is smaller than the 900 that we actually got from our sample. And what we've done when we calculated this is we standardized it to a z, and we come up with that piece right there. And we will go to SALT to find that answer. So bear with me while I switch. Excuse me. Okay, and since we are using our normal curve on this one, we will go to our distribution calculator, and we are going to use our normal distribution. I can do this a couple of ways, and I probably will do this just so you can see we get the same value depending on how we do this. If we're doing the standard normal, that means we have a mean of 0, standard deviation of 1. That would mean I'd want to put in that negative 28.28 and however many digits you want. And you'll see that we do get a probability of 0, which we kind of talked about. Since it is so far, so many standard deviations below that mean, it makes sense. Okay. The other way we could have done this one is using the 1,000. So using that hypothesized mean, the 1,000, and our standard deviation being that 20 divided by the square root of 32. So I'm going to quickly get that number. So 20 divided by the square root of 32 is 3.535533,906. Okay. And then we're going to do what is the probability that we are less than the 900 that our sample was. Now, again, we're getting at the 0, which is what we thought, but you'll also see the z-score popping up right there. So our test statistic kind of is calculated for us. So if you're not real good at calculating that test statistic formula, you can do it this method because it will calculate it for you. So, but you do have to remember the sigma divided by the square root of n when we're doing this. So I'm going to go back to our screen so we can finish this problem off. Okay, and we got a probability here to be about 0. All right. So step 5 is our last piece. So step 5 is we have to make a decision whether or not to reject our alpha. And the rule is that we will reject H naught if the p-value is smaller than the alpha value. So if our p-value is smaller than the alpha, we will reject H naught, because basically our alpha is setting up our boundary. So alpha is the area in the tail for our boundary. And if our p-value is smaller, that means that it is in this area down here. I like to think of it as almost like a rejection area or rejection region. So our sample is completely contained in that rejection region. And in this case, 0 is smaller than that 0.05. So we will reject H naught, which means we believe that there is enough evidence. So our conclusion, and I'm going to run out of room on this piece of paper, is there is enough evidence, or some people like to use the word significant instead of enough, to show that the light bulbs last less than, I'm going to run out of room, 1,000 hours. Okay, so we're basically finding, is there enough evidence to support this, or is there not enough evidence to support that? So are we supporting that they are guilty? Are we not supporting that they are guilty? We never, ever, ever prove that this is true, because it might not be exactly 1,000, it might be 999. We don't really know. All we were trying to prove is if this was true or not. Let's do another example going through those 5 steps. And again, we will, and I'm going to do just 2 more examples here. I have 3, but running out of time. So we'll go through 2 more examples. So we have this researcher thinks that if mothers use vitamins, the birth weight of babies will increase. The average birth weight of the population is 8.6. They're going to test to see if they take these vitamins that the babies do get heavier. So they took 45 mothers, gave them these vitamins, and they found the average to be 9 pounds, which is more. But is it significantly more than the 8.6 to try to change the rules and say everybody should be taking these vitamins? They also have a sample standard deviation of 2.1 pounds. Can you say at 0.05 that these vitamins do increase the baby's birth weight? So again, step 1, we write our hypotheses. So our null and our alternative, we are talking about the average of something. So we're talking about mean. So we're saying the average birth weight is known to be 8.6 pounds because when every baby is born, they are weighed. So we have a pretty good idea of what the average birth weight of children are. But he says that if they take these vitamins, these babies are going to be heavier. So more than. There's our step 1. Step 2 is to determine what test we're going to use. So this is where we're talking about mean. So we look to see, do we know the standard deviation of our population? And if you read through our problem, the only standard deviation we have is the sample. So this is not known. So that means we will be using a t distribution. You'll also remember that in the t distribution, we have a t curve for every single n value. So we don't necessarily have to have more than 30 in our sample, but we have 45. So we'll just kind of make note that our sample size N is going to be that 45. Step 3 and step 4 are going to be done for me using my software. I could, if I'd wanted to, calculated my t-score, that standardized t-value, by taking my x bar minus my mu 0 all over s over that square root of n. So we could do it by hand. We had an average of 9. Mu 0 is this 8.6. My S is my 2.1. And my N is that 45. So I could get this value. I'm going to let my software do it for me. And my software will also at the same time calculate my p-value. So I'm going to go and show you how we calculate this using SALT. And we'll do this for these couple examples so you'll be able to figure it out. So I'm going to go to SALT. I could use my t-distribution here in the normal in here and go to my t-distribution and then use my test statistic here. However, I find it a lot easier because to use the inferential statistics. So I'm going to go into inferential statistics, okay? And we are doing a one sample t, because we took one sample of our pregnant ladies, our 45 pregnant ladies. There are many, 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 many. We do have two sample T's, which we will not get into. We will talk about a two sample proportion. We do not get into the paired T either. So some things to kind of look forward to if you continue on in statistics. So we're using our one sample T. The first thing we're going to be putting in is the sample information. So the sample mean, that was our 9 pounds. Our sample standard deviation was 2.1, and our sample size was 45. So all of the sample information goes in here. The next thing we do is we put in that hypothesized value that we thought, that mu 0 value, so that 8.6 that we wanted talking about. And then we're going to click what the alternative hypothesis was, and ours was a greater than. Because this will then make sure we're looking at an upper tail, as we're going to the right, and find the correct p-value for this situation. Once I have this, I'm going to generate my results and I'm going to look at all my information. So first of all, the thing that I double check is my hypotheses that they wrote. You'll see that it is the equal to versus the greater than, which is exactly what I had written on my paper. So I always double check to make sure that the number is there that I wanted it to be there, so that I didn't get these two things mixed up. I looked down here to find that my sample did have 45. It had a mean of 9, a standard deviation of 2.1. The standard error, that's going to be that 2.1 divided by the square root of 45. So that would be this number here. Our degrees of freedom, n minus 1. And here is our test statistic. So that is step number 3. So from SALT, I'm going to pull that value off, 1.277753. And I'm also going to get step 4. I'm going to pull off my p-value from here, which is 0.104018. So I get my test statistic and the p-value associated with it. Okay, in the days of tables, finding p-values was very, very difficult to do when dealing with a t-distribution. Now we have wonderful software that generates this p-value for us over and over and over again, which is also the reason the p-value method is starting to take over from what used to be the critical value or value method. I'm going to go back to our screen so we can finish this question off, because we still have to make our decision and write our conclusion. So we're going to go back and we're going to let it update here. Okay, so from SALT, it actually calculated this wonderful number out for us, so we didn't have to. You could have. And we got that 1.277753. We also had our p-value that came from SALT. I'll write this on here so you have it. Okay, the other thing we look for in step 4 is the alpha value, because we go back into our question and our alpha was the 0.05. Okay, so we got all our information, and now step 5 is to kind of put it all together to make our conclusion. We're going to compare our p-value. Is our p-value smaller than our alpha value? So here's our p-value, 0.1, 0.05. The answer to that is no. So we do not reject H naught. In other words, okay, what we've just kind of shown is that there is not enough evidence to show that by taking vitamins, or at least these vitamins, the birth weight of a baby will increase. From that 8.6. So in other words, the vitamins, we saw an increase. I'm not going to say we didn't see an increase. We did see an increase from 8.6 to 9. However, that amount of increase was not significant enough to change the status quo. Okay, so in other words, we're not going to all of a sudden start having all of our pregnant mothers start taking these vitamins to get bigger babies, because we didn't have enough of an increase to say that there was a good result. Okay, we're going to do one last one just so we can go through this process one more time and get back, go into SALT again and go through that one more time. So we have a certain group of preschool children under the age of 1 spent on average 30.9 hours per week in non-parental care. So maybe daycare, grandma, or something. A study of state university-based program indicated that a random sample of 32 infants spent on average 32.1 hours per week in their care. The standard deviation of this sample was 3.6. They want to know at alpha 0.01, so a very small alpha value, is there enough evidence to conclude a difference from the national average? So they're kind of saying, okay, we think that our college is different. Okay, not bigger, not smaller, but just different. All right, so step number 1. We're going to go through our 5 steps again. Now, again, I'm saying that this is things that they do go through in a situation like this. A lot of times they will actually start with a hypothesis and they'll say, oh, we think we're different. So then they go back and get the sample. But usually this is the first step, as they say, okay, we know that the nationwide is 30.9. We think we're different. So we think our average is not 30.9. We think it's different. Then they go and get their sample and so forth. But they can even do step 2 before they even do the sample 2, because step 2 indicates, well, do we know our national standard deviation? The population standard deviation. The answer to that is no, sigma is unknown. So we know we're going to be using a t. Okay, a lot of times remembering the bigger the sample we get, the better it's going to be for us. That's another reason we want to make sure to have large samples, because we get better results with larger samples because we get a better estimate from our sample. All right, step 3 is to find that test statistic, which would be in this case a t-value. And again, I'm going to use SALT to find it. I'm also going to, at the same time, do step 4. Step 4 is to find my alpha value and my p-value. P-value I will get from SALT. Both of this I'll get from SALT. This I also get from SALT. Or whatever statistical package you are using. The alpha value was chosen for us in the problem to be 0.01. So I'm going to go back to our statistical program, which we use SALT in my class. That's what my students have access to. And we are doing a one sample t. Our sample mean, so that was our 32.1. If I go back into the question to find my sample mean, I find my sample standard deviation to be 3.6. And my sample size was 32. We took 32 people. The hypothesized mean, this is the 30.9, the nationwide piece, and we are thinking not equal to. So this would be considered a two-tail test because we're looking in both directions. And when they calculate the p-value, they are actually looking at both tails. So they're looking at both sides. I'm going to generate my results so that it does change the pieces that I see. So again, I kind of look at my hypotheses, mu equal to 30.9, mu not equal to 30.9. That is what I had on my paper. There's my 32 people that we had that had an average of 32.1, standard deviation of 3.6. If I calculate the standard error, I would get this value, which is that 3.6 divided by the square root of 32. The degrees of freedom, 31. My test statistic, that's my step 3, 1.88568. And knowing what we've known so far, we're 1.8 standard deviations below. So we're between 1 and 2, closer to the 2. And my p-value for that value is a 0.068748. Not that we need all of the digits, but I'm just writing them down so that if you do this problem later and you go and do it yourself, you can compare what you get to what we had gotten this time. So just so you know what we had. All right, we're going to go back to our camera one last time to find our results and to make our decision and so on and so forth. So here was our test statistics, which led us to this p-value. These two kind of do go hand in hand, because if you're thinking about our t curve, there's our value up here. The p-value is actually the probability in both tails, because we could have been up here or down there, so it's kind of allowing for both directions. But step 5, where we make our decisions and write our conclusion, we look at, is our p-value smaller than the alpha? Is our sample in that rejection region? So if I set up a 0.01 up here, is this completely contained by what we've set the boundaries to be? And the answer to that is no. So we will not reject our null. In other words, there is insufficient or not enough should have went the other way. There is not enough. Yes, my spelling is not good, so we are not going to spell insufficient today. There is not enough evidence to show that the university center-based program has a different, I'm going to write number of hours than the national. And this is worded kind of poorly because I did it on the fly here. Every time I write my conclusions, they're a little different, and sometimes they're really good and sometimes they're not. I am not a published statistician, so they are a little weak. You will read better ones in our homework. You'll see better ones in a textbook. You'll see better ones in research publications. So, but it kind of gives you an idea. So when you are reading your research publications and they tell you that there's not enough evidence, now you can kind of understand the process that went into coming up with that situation. So if you're going into healthcare or human resources or any of area where you are going to be reading research, now you'll kind of understand what process went into that one little sentence. All of this stuff that we've been talking about all semester long leads up to that one sentence. Hopefully, I will see you in the last few videos that we have. I have a couple left for this course, and I look forward to seeing you in those videos. Have a great day.